very common and popular application of DC-DC converters is in battery charging. Battery chargers are made of switched mode DC-DC converters. So you see that here is the battery which needs to be charged. That battery, of course, will be used to drive some load. Now this battery is interfaced through a DC-DC converter with some DC source. Now that DC source could be a fuel cell, or it could be a mains grid followed by a rectifier, or it could be photovoltaic cells, very popular photovoltaic cells charging the battery, or wind hydro system connected to an alternator or a generator followed by a rectifier which is used for charging the battery. So there are very many sources which can be used as the input source which can be used to charge the battery. And as far as the DC-DC converter is concerned, you could use any DC-DC converter. It could be the buck, the boost, the buck boost converter. And we have discussed the isolated converters like the forward converter, the dual switch forward converter, push-pull converter, half-bridge converter, full-bridge converter, flyback converter. All these converters are possible candidates to be used for the DC-DC converter to charge the battery. We have seen that in a DC-DC converter, the output voltage, the voltage which is across the output of the DC-DC converter can be regulated, and we also saw how to do the closed loop operation. In this application, the battery charging application, we need to control the charge current that you are pumping into the battery. So it is a slightly different nature of control where you are controlling the current, the output current, I0. Of course, in the case the DC-DC converter, if it is a buck converter which is used, the output current and the inductor current are the same. But in many cases, the inductor current, that is the state, is controlled, and which will indirectly control the output current. If you are using a boost converter, the inductor current, which is the input current, will be controlled. In the case of the buck boost, the inductor current is controlled. Generally, for battery charging, the charging current which is being pumped into the battery needs to be profiled. So if it is properly profiled, then the chemistry in the battery will work properly to extract as much life out of the battery as possible. However, what we will be discussing is not just output current control. We will be discussing the inductor current control, that is controlling the inductor state using any one of the converters, the buck boost converters. The concept of current control is similar whichever be the converters. I will initially explain with the buck converter using let us say photovoltaic cell input as the source here, being the one of the most popular and growing application areas. You can use it with either the boost or the buck boost or any other converter also. So let us discuss the DC-DC converter operation with current control, controlling the inductor current. So in the case the buck converter that I will be discussing, the inductor current control and the output current control will become same. Some of the advantage of current control is that there is inherent overcurrent protection. So cycle by cycle instantaneous overcurrent protection can be achieved with current control. Another nice advantage, spin-off benefit that you would get from current control is that no flux walking will happen. You don't need a flux walking capacitor. And that is a significant benefit, because as you start going for higher and higher powers, the capacitor can become significantly costly in order to prevent flux walking. So let me consider a photovoltaic cell as the source, because it is a very popular source now. Rooftop solar PV cells becoming more and more popular, and many applications related to photovoltaic cells are involved in charging the batteries. So I will replace the generic source with a photovoltaic cell. You may use any of the voltage sources, but I'm just using a photovoltaic source. It may as well be a mains grid rectifier, which we have dealt with much earlier in the course. So this photovoltaic cell is used to charge the battery through this DC-DC converter, and the DC-DC converter will be a buck converter that I will be using. You can use any primary converter, and we will be sensing the output current, which will be the inductor current, and use that to control the current of the inductor. So let me mark this. This is the terminal voltage of the source. IPV is the current input current to the DC-DC converter. So now let us see how this battery charger is built. Let us try to understand the principle of operation, and then let me go into the circuit and give you the schematic for controlling the DC-DC converter for current control. And later I will be explaining some problems that we will also later address by providing slope compensation. Let us now discuss the battery charger circuit, where MPPT is integrated inbuilt into the charger scenario. So let us consider this PV module or a PV array, and this PV array is connected to a DC-DC converter, and then the output of the DC-DC converter is connected to a battery that needs to be charged. So you will say this is the DC-DC converter. It has a control input D, the duty cycle input. The voltage across the terminals of the DC-DC converter output is connected to the battery, and therefore the output of the DC-DC converter, the voltage is fixed by the battery, because the battery is a source. Across the battery you may have a load connected like this. So you have a load connected like this. Now, how do we charge the battery? The terminal voltage is VB, and this voltage is defined. Then what would be the current, charge current? So let us say we want to put the peak power from the panel into the battery. Now let us say PM is the peak power. PM by VB will give you the IB, the peak power that is going out of the DC-DC converter. So IB can be controlled by controlling the duty cycle, because VB is fixed, and therefore power can be controlled by controlling the duty cycle, as VB is fixed. So that is the strategy that we want to adopt. Sense this current I0, which is flowing out of the terminals of the DC-DC converter, and use that as the feedback. You also provide the PV current, IPV, and also the terminal voltage of the PV, VT, which will be used for sensing the power that is being drawn from the PV module. Now, what is the control algorithm that you need to put in here? Let us consider this boundary here, the terminals of the DC-DC converter to which the battery is connected. Now normally if you consider these terminals and the battery is connected here, all this portion PV source DC-DC converter can be considered as a controlled source. Now let us say if it's a controlled voltage source, plus and minus like this. If you have a controlled voltage source, you cannot parallel two voltage sources because there is no impedance in between, and there can be huge circulating currents which can blow up something in the controlled voltage source. So whenever you are having a controlled voltage source, you need to have a series impedance which will limit the current. So if you are having a controlled voltage source, have a series impedance. This is one possibility. But you don't want to control the voltage because the battery voltage is fixed. You can directly control the current. In fact, a controlled voltage source with a series impedance, and if the impedance is inductive, non-dissipative, that will form a controlled current source itself. So what can be also done is across this boundary where you have the battery, you have a controlled source, and that controlled source you make it as a controlled current source. It has the inbuilt impedance, necessary impedance inbuilt within it, so that there will always be a current limit. Current source and the voltage sources can be connected in parallel. So we will follow this model, and that is what we will introduce into this control algorithm, which is a current controller. Let me draw and discuss the schematic for a buck converter based current controlled battery charger. Now what it basically means is that the PV module or the PV array is interfaced with a buck converter which will charge the battery. So let us draw the circuit schematic. So you have the PV module, PV panel connected to a buffer capacitor CT at the terminals, and this is followed by a buck converter. So I have a BJT switch. Now this BJT switch can be replaced with a MOSFET switch or an IGBT switch, power semiconductor switch, followed by a diode, and I have an inductor, and following the inductor I am not going to place a capacitor. Instead of the capacitor I will connect a battery in this fashion, and across the battery you may have the load or not like this. So because the battery here fixes the potential across the output terminals of the DC-DC converter, the current through R0 is decoupled from the rest of the circuit operation. So the current I0 through R0 is V battery by R0. Now here you have the battery voltage VB, we will call that as VB. The current through the inductor is as shown here. This will be the current through the battery, IB, and this current will be I0, which is flowing through the external load. Now our point of interest is this current. The current that is going to the battery load combined should be such that maximum power is drawn from the PV array or the PV module. So let us draw the control schema. I have a comparator here, plus, minus, so it compares the feedback signal with the reference signal. I will call the feedback signal as IL. So what I am going to feedback is the current. Recall our discussion, voltage VB being constant because of the voltage source connected across the terminal. It is sufficient to feedback just the current and use that one to control the power. And here you will have IL reference. reference for this. Now this error goes through a comparator. So I will connect this to the minus terminal, to the plus terminal I connect ground 0. Of course there is power supplies for the comparator. The output of the comparator goes to an SR latch. So I am going to connect the output of the comparator to the R reset pin of the SR latch. There is a set pin also, and there is a Q, the output pin of the SR latch. The output of the pin of the SR latch is going to get connected to this gate drive circuit or a base drive circuit in this fashion. So output of the SR latch Q gets connected to the base drive circuit, which will drive this on or off. So how does this operate? Before that, there is something we need to connect to the set pin also. So let me have a clock block. So the clock output is connected to the set pin of the SR latch. How does this clock look like? So let me have the time. So I will mark the sticks. Each of the stick space is the switching time period TS. Okay, so the clock is in this fashion. At the beginning of every switching time period, you will have a very narrow, very small duty cycle pulse coming like that at the same period, the period being defined by this clock. So the moment this small duty cycle pulse comes to the set pin, it comes and sets the output of the latch on the rising edge. So you have the rising edge. So at the rising edge, we see that Q gets set, and at every start of the period, Q is set and then switches on the transistor. Now let us look at the various waveforms to understand how this operates. So I will draw the various axes, time axis basically, and I will divide this into two portions. This is the first cycle TS, and this is the later cycle. So at the start of the cycle, you have a small duty cycle pulse, and that is this clock pulse, and it happens at every starting of the period. Now the moment this clock pulse is given, it sets this SR latch. Q is high. Moment Q is high, there is base drive for the BJT or gate drive for the MOSFET, and this is on, and VT gets connected and the inductor is charging up. The inductor current is growing. Now let me set some reference here. Let me for the moment set a reference which is constant. Okay, clock. Then I will set a reference which is constant IL reference. So when Q is high, it is providing the base drive or gate drive to this power semiconductor switch, and thereby the inductor current is integrating and having a positive slope, and that positive slope is V in minus VB, V battery divided by L. So it keeps increasing in this fashion. IL ref is higher than IL. This is IL ref, which is higher than IL. So when IL ref is higher than IL, the output of this algebraic summer will be positive, but that is connected to the negative of the comparator, and the output will be low. The reset pin will be low. No change on Q. So it keeps increasing till the point when IL reaches and crosses over IL ref. So the output of the algebraic summer becomes negative, and this becomes positive. Reset becomes positive, and therefore Q will reset and go low. The moment Q goes low, there is no drive for this power semiconductor switch, it will switch off. And the inductor will start freewheeling and start falling. Current will start falling. So if you take this portion of the operation, you will see that if you look at the output of the Q of the flip-flop, it would have been high till this point and then it resets. So during this period, when this is low, inductor is freewheeling, you know the buck converter operation, it is freewheeling. This is connected to 0 because it is freewheeling like this, and what is connected to the inductor is minus V0 by L, or minus V0 in this case is VB minus VB by L. And then again at the new cycle, there is a clock coming in. This will trigger the SR latch, Q goes high. The cycle repeats. So you will have the inductor current rising, and then at the point when IL reaches IL ref, there is a change in the slope. So it keeps happening in this fashion. So observe that whatever current value you are setting, IL ref, the inductor current, the current that is going to the battery load combined, never exceeds the IL ref. So it is always below the IL ref and gets controlled in this fashion. And this is called current control. It is as though every cycle there is a check for the currents, and the moment there is a overcurrent within a cycle, it is switched off. And then again the power semiconductor switch is switched on the next cycle, and then it is on till the point when the current exceeds the reference current, and again it switches off. So on it keeps doing, and cycle by cycle there is current limiting, and therefore this is a very safe and fast method of doing battery charging through current control mechanism.